Okay, in this exercise, let's say that we have this platform that is revolving around, and we have this button on it that is we don't want to fall off. So just looking down on the top of a platform, basically we have something like this, and it's rotating around with some speed, some angular speed, which we'll talk about later. Here, and it's rotating around, and you can imagine that if I put a little button right here in the middle, that it doesn't slip off. It just kind of rotates around. This thing just spins around, right? And its circle is not very big. It just kind of turns around there. If I put it a little bit farther out, then it takes this kind of path around like this, right? And it's a little bit easier to fall off here. If I put something all the way on the edge, then it falls off even easier, right? And so there's a relationship between how far away we put it, and how fast it's going, and the acceleration needed for it to maintain a circle, right? Basically, every in every one of these cases, we have an object which needs to maintain a circular motion, and so therefore it must have some sort of centripetal acceleration towards the center, right? So this thing must be accelerated towards the center, and if it's out here, it's going faster actually, and so it needs to have an even greater acceleration towards the center. Because clearly, you have the same time, right? For one rotation has the same time, and out here at a larger radius, it has farther to go in the same amount of time, so we have a bigger speed, right? So we know that centripetal acceleration, this is v squared over r, right? So as the radius gets bigger, the centripetal acceleration gets smaller, but the speed also goes up as we go farther from the edge. The speed goes up, and then because the speed is squared, we actually need a larger acceleration the farther it is from the edge, or from the center, closer to the edge. So we need to find here the coefficient of static friction between the button and the platform in order for this button, which is placed 0.15 meters from the axis. This is the axis of rotation, kind of like it goes right into the screen here. And so it's 0.15 meters from the axis, and it rotates at 40 revolutions per minute. This whole thing with the button, being placed on a wheel with a diameter of 0.32 meters, that doesn't matter. We don't actually care how big the wheel is. We care about how far away the button is from the center, or really how big is the circle that this button has to stay in. That's what dictates whether or not it's going to fall off. Okay, so the way that we do this, and it can be a little bit kind of confusing at first to say, okay, so if this thing is over here, if my button's here and it's rotating around, how do I ever stop to analyze the forces, right? Because we need to analyze the forces, the coefficient of static friction, right? This is related to our static friction force, right? So we need to know what's the static friction force, and then we can go backwards from there to figure out what the coefficient of static friction is. But you might think, okay, so how am I going to analyze these forces when this thing's always moving? What we do is we just take a snapshot. It's going to be the same at every point on the circle, so we can just take a snapshot when it's like right here, or maybe I'll take a snapshot when it's right here. Okay, and I'm going to kind of rotate this table up, so that I'm looking at a bird's eye. Now I kind of want to look at the side. So let me kind of take this table. Here's my rotating platform like this, and here's my button. Okay, right there, my little snapshot in time. That's where the button is, and then we have our axis of rotation. It's going through right there. It would be just like this, right? That's our axis that's rotating around this, right? So we have it's kind of rotating around that axis there. And we know the distance. This is 0.15 meters, so I'll go ahead and put that in there. So this is 0.15 meters here, and we're told that it's rotating at 40 revolutions per minute, right? So this is the same thing as, well, actually, we'll come back to that in a minute. So part A wants us to find the coefficient of static friction. There's a part B, but let's focus on part A. So we talked about it already. We need to analyze the forces acting on it, right? So I should free body diagram this button here, so I can find out, this static friction force acting on it. So a free body diagram of the button. And the free body diagram, when I'm taking a snapshot right here, and I have something like this, forces that act on it, there's the weight of the button, right? There's weight right there. There's a normal force acting upwards, right? And there's clearly, if there's a coefficient of static friction, there must be some static friction force, right? And the direction of this, at least at this snapshot, you can think, all right, what must be the direction of our frictional force? If I have to have this thing accelerate towards the center, when I take a snapshot here, the center is to the right, and this must be my centripetal acceleration. And so the only thing I have to provide that centripetal acceleration is the frictional force. So I must have the static friction right here. Okay? I don't have any string attached. I don't have, anything else other than just friction to push it towards the center. And you might ask too, why is it the static friction force? This thing is moving, right? I mean, it's going around in a circle. Well, it's, which coefficient of friction we use is dependent on how the surfaces interact, right? This button is staying fixed relative to the platform, right? It doesn't move. It's not sliding off the platform, or at least that's what we're hoping. That's what we're solving for. But the table itself, the platform itself, is rotating around, but the button doesn't move relative to that. So we use, the static friction force and the coefficient of static friction. Okay. So there's a free body diagram of our button, and we want to know this static friction force, right? So we know that it's not accelerating into or out of the platform, right? Hopefully it's a solid enough platform to not be accelerating into that. So we can just start with sum of forces in the y direction is equal to 0, right? Because the acceleration in the y direction is equal to 0. Oh, coordinate system. I set this up so that I can have a coordinate system this way, x, y. That's why I decided to take a snapshot right here, actually. So I can just have x is that way, y is coming out of the screen. Okay, so sum of the forces in the y direction equals 0. So this means that the normal force minus the weight is equal to 0. And so we have the normal force is equal to the weight here. Okay? And then when we look at the sum of the forces in the x direction, we have to have an acceleration in the x direction here, and it's very specifically our centripetal acceleration, right? So this is the mass times the centripetal acceleration, which is equal to, just mass times centripetal acceleration. So then we're going to have, the only force in the x direction is our static friction force, right? Fs is equal to MAC. Okay? But the static friction force is the coefficient of static friction times the normal force, which is equal, the normal force we just said was mg, right? So this is coefficient of static friction times mg is equal to mass times the centripetal acceleration. Okay? And then we have, masses on both sides here. We can cancel this out. And we have the coefficient of static friction times gravity is equal to the centripetal acceleration. So wanting to solve for the coefficient of static friction, that's what they asked us to solve for. So what is the coefficient of static friction? Then we have, just algebraically, the coefficient of static friction is the centripetal acceleration divided by gravity. So the only thing is, what's the centripetal acceleration? Because we know g, right? And there's a couple of ways that we can formulate the centripetal acceleration. We've seen so far centripetal acceleration is equal to the speed squared divided by the radius, which I have the radius, 0.15 meters. I would just need the speed. Or this is also the same as 4 pi squared r over t squared. And we derive this from, finding the speed from, circumference divided by period, right? So this t is the period. This is probably the easier way to go about it, given the information that we have. We can find this period as the time for one revolution, right? So they gave us here the revolutions per time. They gave us 40 revolutions per minute. So 40 revolutions per minute, I can just take the inverse of this and get minutes per revolution. Although we'll need it in seconds, right? Because everything else is in, standard units, right? Which will have seconds for time. But if we have the speed, this is called angular speed, which we'll talk about more later, 40 revolutions per minute. If I take the inverse of this, that's going to be 1 over 40 minutes per revolution, right? I mean, if it takes 40 revolutions, or if I can get 40 revolutions in 1 minute, then it takes 1/40th of a minute for a revolution, right? So 1/40th of a minute per revolution. But let's do seconds. And I know that a minute is 60 seconds, right? And so I can say here, this comes out to 60 over 40 seconds per revolution. Okay? So 60 40ths of a second per revolution, or this comes out to, was that 1.5? 1.5 seconds per revolution. That's what we get, for 40 revolutions per minute, means 1.5 seconds for each revolution, which this is what the period is. Period is the time for one revolution. So this is 1.5 seconds. Okay? And the rest of this stuff we can just plug in. Radius was 0.15 meters, right? And so we can just plug into what we had over here. The centripetal acceleration divided by g. That was a highlighter, sorry. Centripetal acceleration divided by g. And so we have the coefficient of static friction is 4 pi squared r over gt squared, which is 4 pi squared times 0.15 divided by 9.8 times 1.5 was our period squared, right? And this comes out to a coefficient of static friction of 0.269, which seems quite reasonable based on, the coefficients of static friction we've used for things in previous problems. Okay? Part B asks us, part B here says, how far from the axis can the button be placed without slipping if the platform rotates at 60 revolutions per minute? So now we're going to use this same coefficient of static friction because in the same friction force, because we have the same button and the same platform, right? And we just wanted to find out what R is based on this new angular speed, which basically gives us a new period. And I think we can see from this one, 60 revolutions per minute, this period is equal to 1 second per revolution. Okay, so the period here is 1. So we can just use the results that we had previously. Let me just I'll go back a couple steps. But here's for B. From part A, we have this mu s mg is equal to m times 4 pi squared r over t squared, right? So we can solve, actually we could have canceled that m out, but we can solve for r. The radius is going to be the coefficient of static friction times g times the period squared divided by 4 pi squared, right? And so then just plugging in, same thing that we got for the coefficient of static friction a second ago. R is 0.269 times g, 9.8, times this new period squared, which is 1 squared, divided by 4 pi squared. And we get a new radius, and this is going to be in meters, right? We use meters per second squared here, second squared here. The rest of these are coefficients, right? So this doesn't have a unit, pi doesn't have a unit, but this is meters per second squared times second squared. This is in seconds. So we get meters. And the radius is 0.067 meters. So 6.7 centimeters. So we speed it up a little bit. We have to move it in. Before, when it was at 40 revolutions per minute, we were able to put it at 0.15 meters, right? 15 centimeters away. Now we can put it a little bit less than half that. So got to be a little bit closer. Otherwise, it's going to end up sliding off, which is probably something we've experienced, if you ever put things on turntables and watch them slide off.